Hello everyone, welcome you all in today's session. As we have discussed the linear span of a set in the last session. So what I said, if you have given a set S as the vectors are v1, v2, so on up to vn are the finite number of vectors, then the linear span of the set of vectors is just like the set of all the linear combination, that's alpha 1 v1, alpha 2 v2, plus so on, plus alpha n vn, where these scalars are coming from the field of the vector space. Then I showed that if you will take S for example as 1 comma 0, it is the subset of R2, and the linear span of this set is nothing, that is the x-axis. Okay, that is the x-axis of R2, and I have already discussed that every vector of this x-axis will belong in the linear span of S. Okay, so if you will take the point for example here as a comma b, this a comma b you can't write it as the linear combination of the vector 1 comma 0, but any point here on the x-axis you can write any vector on the x-axis as the linear combination of the point 1 comma 0. For example, if someone will give you the vector, let's say 9 comma 5 or 9 comma 0, and he asks you that write it as a linear combination of this vector 1 comma 0, so you will directly write 9 times 1 comma 0, so it is alpha times your vector v. So alpha is here the scalar, that's 9. So similarly, for example, if you have the R2 as a vector space, then any line here, so for example you will take it, so the vectors we generate this line, the linear span of that vector will be this line. For example, if I will give you that S is equal to 1 comma 2, check its linear span, that will be alpha times 1 comma 2, where alpha is any real number, so it will give you the alpha comma 2 alpha, so that is alpha belongs to R. So it is same that y is equal to 2x, isn't it? If you have the coordinates x comma y, so it is same y is equal to 2x, so that's the line here. So that means any vector here on y is equal to 2x is, if you will take any vector on this line, that can be written as a linear combination of this vector 1 comma 2. Similarly, for example, if you have the vector 0 comma 1, you know the linear span of S is the y-axis, and if you will take the S to be 0 comma 1, 0 comma 2, and the linear span of this will be alpha times 0 comma 1, so that is the linear span, plus beta times 0 comma 2, where alpha and beta will be from the real line, so it will give you 0 comma alpha plus 2 beta. So these are the points on the y-axis, and this will be the real number, and any real number you can write as the linear combination of this 1 comma 2, or here as alpha plus 2 beta, so it will be any real number R. So it is again your, that is y-axis. Okay, so you can check that these two vectors spans this set, and this vector also spans the y-axis. If you will check 0 comma 1, 1 comma 2 spans the line that's passing through 0 comma 0, and whose equation is y is equal to 2x. So this is the span of the set. But now we will discuss one another concept, that is the basis. What is basis? The basis is the subset of the space the subset of the space such that that basis or the set of vectors will generate whole of the vector space. Okay, for example, if, or I will write it this way, let S is equal to, or B is equal to V1, V2, so on up to Vn, be the set of vectors of the vector space V over F. Okay, we say B is the basis of this vector space V over F if the following condition hold. If the following conditions hold. The first condition is that this B, so the set of vectors B is equal to V1, V2, so on Vn, be linearly independent. These set of vectors should be linearly independent. And second is that the linear span of this B will be your whole vector space. Means every vector of the vector space can be written as the linear combination of these vectors. Linearly independent, you know, that is alpha 1 v1, alpha 2 v2, plus so on, plus alpha n vn will be 0 only when your alpha I will be equal to 0. Means all the scalars are 0. It is only possible to make this linear combination equal to 0. So what is the difference here? So here we are actually taking the linear span again, but this linear span is your whole vector space. Also the set of vectors is linearly independent, and you have to remember this is the smallest. Okay, this is the smallest, this is the, or we can say smallest set or subset of V of F, smallest subset of V of F that spans the vector space and is linearly independent. Okay, so that means it is the smallest linearly independent subset such that it spans whole of the vector space. This is the first condition. Second is that it means that any linearly independent subset that is smaller than B cannot be the basis. Cannot be the basis. And it is also the largest linearly independent set. Also you can say it is the smallest set that spans your vector space V of F. Okay, for example, if you have the vector space R over R, if you will take the set S is equal to 1, the linear span of S will be alpha times 1. Alpha is any real number, so it is same as alpha. Alpha is any real number. If you will take the definition of real number, what is that? So x is a real number, isn't x is a real number, so it is same, so it spans your whole R. Okay, so even you can check that if you will take another set, let it will be your another set S prime. If you will take 1 and 2, so its span is again the little line, that is alpha 1 plus beta 2, so that is your alpha plus 2 beta, and alpha and beta will be again in R, and you know sum of the two real number is again a real number, so it will be some gamma, and gamma is a real number. So it also spans R, but this 1 and 2 are not linearly independent, because if you will write alpha plus 2 beta is equal to 0, you will find that alpha is, or 2 beta is equal to alpha, that is beta is minus alpha, so beta is equal to minus alpha by 2. So one vector is here the linear combination of other vectors, so it is linearly dependent, isn't it? You got the solution here, that's non-zero. For example, you will give alpha is equal to 1, so beta will be minus 1 by 2. If you will put it here, it will be 0. So you got the non-zero scalar such that it will be equal to, so it is linearly dependent. But what is the basis? It should be linearly dependent and spans your whole vector space, and you can check it, it spans whole of your vector space. And also you will check that this 1 is not equal to 0, and that means alpha 1, if you will multiply, it will be 0 only when alpha is equal to 0, so that is linearly independent. So the basis for your real space, that is the R, is this S. Similarly, if you will take R over R, this is the example here. If you will take here the set, let's take B is a set whose elements are 1 comma 0, 0 comma 1. You know what are the elements in R2? Sorry, R2 over R. So R2 has the elements x comma y, such that x is a real number and y is a real number. So if its span is your R2, then its dimension, that is the number of vectors in the basis, should be 2. Okay. So let's check first the linear span. Linear span of B is nothing, that is the set of linear combination to alpha 1 comma 0 plus beta 0 comma 1, and alpha beta are the real numbers. That is, it will be alpha comma beta, alpha is a real number and beta is a real number. And if you will check, it is the same definition, so it is your R2, isn't it? Now check whether these are linearly dependent or independent. So here you can make this B, you have the vector v1 and v2, just directly take the determinant, so that is 1 0 0 1 when you have the square matrix, so it is not equal to 0, so it is linearly independent. Otherwise you can do here this matrix 1 0 0 1, you will check its rank, if it is a matrix A, its rank is equal to 2. It is already in the echelon form, so its rank is 2, and you have the two unknowns alpha and beta, so it means that it is equal to number of unknowns, so it means that it is linearly independent. You have checked this B is linearly independent, and it spans your whole R2, means every vector of R2 can be written as a linear combination of these vectors, so it means that B is the basis. B is the basis of R2. And what is dimension here? I will note it. Dimension means the cardinality of the basis of vector space is called the dimension. How many vectors you require to create whole of your R2 is 2, so that means dimension of R2 is equal to 2. Okay, so here what is the dimension? You required only one vector, that's 1, so the dimension of a real line is your whole 1. Okay, that's 1 only. Similarly, if you will take, these are called the standard bases. So E, you can check your 1 comma 0 as E1 and your 0 comma 1 as your E2. These are called the standard bases. Similarly, if you have R3 over R, if I will give you the vectors, for example, let B is the set of vectors 1 comma 0 comma 0, you know it is in the R3, 0 comma 1 comma 0 and 0 0 1, you will check it is the basis and the dimension is here, that's 3. Similarly, so actually the linear span of B will be, gives you that alpha v1, that is 1 0 0, plus beta 0 1 0 plus gamma 0 0 1, and these alpha, beta, gamma are the real numbers. So it will give you alpha, beta, gamma. Alpha, beta, gamma are the real numbers. You know this is nothing but your R3. So it spans off all of your vector space. Similarly, you can make a matrix B. So that is 1 0 0 0 1 0 0 0 1. If you will check the determinant of B, since it is a square matrix, you can go through the determinant as well. So that is non-zero, so it is linearly independent. So both the condition hold. It means B is the basis. B is the basis of R3. And what is the dimension? Dimension is equal to 1 vector, 2 vector, 3 vector. So the dimension is 3. For example, I will give the one space here. Let X is the space whose elements are in the form of x comma 2x, which we have defined in a line. So x is, or x comma y, where x is or y is equal to 2x, and y and x are both the real numbers. Now what is the basis for this one? You can check, you can write it into the x comma y is 2x, so x is a real number. So you can check that you have only one required in this variable here. So what you will do, if you will take any vector in the form of 1 comma 2, gives the x as a value 1, and check its linear span. If you will check the linear span of B, you will get alpha times 1 comma 2. Alpha is any real number, is it? So it will give you alpha comma 2 alpha. Alpha is any real number. So it is the same definition, only the difference is that in the notation. So it is your x. So what is the dimension of this x? That is 2. First you have to check whether it is linearly independent or not. So you have only one vector, v1 is equal to 1 comma 2. Since it is non-zero, so that means alpha v1 will be equal to 0 only when your alpha is 0. So it is linearly independent, and its span is your whole set. So it means that this is the basis, this is the basis, and its dimension will be only 1. Okay, its dimension is only 1. So you have gone through the basis and the dimension. Let's go through the basis for the matrix set, so which we have defined it M2 cross 2 over R. You know the sets are here in the form of A, B, C and D, and A, B, C and D are the real numbers, is it? So let's go take a set of the vectors here. The vector we will take 1 0 0 1 or 0 0 for this A, and another we will take 0 1 0 0 for this B. I will take 0 1 0 0 for the C, and 0 0 0 1 for the D element. Okay, I took these 4 elements from the M2R. You can check it is from M2 cross 2 or the subset of this. Now check the linear span of B. What is that? The linear span of B is alpha 1 v1. This is what v1, that's 1 0 0 0 plus alpha 2 0 1 0 0 plus alpha 3 0 0 1 0 plus alpha 4 0 0 0 1. These alphas are from the real line. So it will give you the alpha 1, alpha 2, alpha 3, alpha 4, and all the alphas are from the real line. You can check your set is the set of 2 cross 2 matrices whose entries are the real line. Here you are getting again a same set whose entries are from the real. So it means that it is equal to your M2 cross 2 over R. So it spans your whole set. But are these linearly independent? So how you will check it is linearly independent or not? So take the linear combination of these to be 0. So that is alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus alpha 4 v4 is equal to 0. So you will get alpha 1, alpha 2, alpha 3, alpha 4 is equal to 0, means 0 0 0 and 0. So that is alpha 1 is 0, alpha 2 is 0, alpha 3 is 0, and alpha 4 is 0, the corresponding elements here. Okay, so it means that all the scalars are 0. It means that it is linearly independent. So that means this set B is the basis for this vector space. And what is the dimension of this vector space M2 cross 2 over R? So the dimension is the number of vectors you require to create this whole vector space. So that is your only the 4 vectors. So that means the dimension is 4. Okay, so the basis is nothing, it is the minimal set. What how many minimum vectors you have required to create whole of the vector space. Okay, in other words, in general, you can say these are the fundamental vectors to create whole of your vector space. How many such vectors you required. Okay, so these are some examples. We will discuss more examples in the next video. Thank you very much.